Hi, and welcome to another episode of Math-Adda with your host Shankudip. So, this week we had a number of entrance exams for the Indian Statistical Institute, and among them was the most basic one, the one for BStat and BMath. And there was a problem that caught my eye. You will see that problem shortly. It's number 6 from subjective. It caught my eye because it could be solved from using some ideas that we discussed in this Math-Adda in episode 1. So in case you have not watched episode 1, please find the link in description. So it can be solved using ideas from episode 1, but it also involves some things that I forgot to mention or I did not mention in episode 1. We are going to take that on today. So let's start. So the problem says that there is a sequence of points on the plane. The points are denoted by capital Pi. And after the first three, which form a triangle, by the way, which is a non-degenerate triangle, which means they are not collinear. After the first three, there is a recurrence relation connecting the other points. For example, P4 is the midpoint of P1, P2. P5 is the midpoint of P2, P3, and so on. So given the first 3 points, you know every other point in the sequence. And you're supposed to prove that the areas of the successive triangles, P1, P2, P3, P2, P3, P4, P3, P4, P5, these areas actually go to 0 as n tends to infinity. Now, as soon as I saw the problem, I thought, hey, this problem is excellent for using complex numbers. So suppose the plane we are talking about is the complex plane or the Argand plane. And small pi denotes the point capital Pi. I mean, small pi is a complex number that corresponds to the point capital Pi. Then the recurrence relation is simply right, and it looks entirely like the type of problem we discussed in episode 1. This is a linear recurrence relation. You have some initial conditions. You can find a characteristic equation. You can solve it. You can find some independent solutions. You can write any other solution, any general solution in terms of those solutions. But there is a problem. Our discussion in episode 1 was about real sequences. This is a complex sequence. Is there a difference? That's what we are going to find out. Before we find that out, we should mention that there was a case in episode 1 which we did not talk about, namely the case of complex solutions to the characteristic equation. And we will see an example where that becomes important. And this example is taken from physics, the case of a spring. So suppose we have a spring which is fixed to a immovable wall, and to the end of the spring is attached an object, and the whole setup is on a plane. There is no friction anywhere, and this object has mass m. Then when the whole system is at rest, there is no force anywhere, we call that position to be x equal to 0. When the spring is elongated, then x is greater than 0, and when the spring is compressed, x is less than 0. It is well known by experimental means, that the force on the object, that box there, it depends on the displacement or the value of x. When x is 0, there is no force. where x is positive, there is a force trying to bring the object back to x equal to 0. And when x is negative, there is also a force trying to bring the object back to the x equal to 0. So x equal to 0 is some kind of an equilibrium point. If you elongate the string, it tries to come back. If you compress the string, it tries to expand. Okay. So the law actually looks like this. F is the force on the box, is equal to minus kx. Why minus? Because the force is always opposing the motion. If you want to go away, the force is trying to bring you back. If you are trying to compress, the force is pushing you away. It's always acting in the opposite direction. That's why it's minus, and that k is called a spring constant. Okay. Now Newton's law tells us that F is equal to m times acceleration, which means m times d2x. dt2 is equal to minus kx, or m d2x So some people, I think, remember from physics how to solve this. The method used there is very similar to what we use in episode 1. This is a linear differential equation, which means that if you have two solutions, x1 and x2, any linear combination of those two is also a solution. So if we can find two independent solutions, why two? Because there are two initial conditions, position and velocity. If we know position and we know velocity, then the rest is fixed. So if we can find that means the solution space is two-dimensional. If we can find two linearly independent solutions, independent solutions, then the general solution is a linear combination of that. And how do you do that? We try to find solutions that have a special form. For example, let's see if we have a solution of the form, say, z equal to e power lambda t. If we plug this in, it actually gives us z is x here, by the way. Z is the function we're looking for. It actually gives us lambda square e power lambda t plus k by m e power lambda t is equal to 0. Now we can cancel e power lambda t because it's always non-zero. That gives us lambda is equal to minus I root k by m. Therefore, the general solution of this equation is x is equal to some constant a e power, oh sorry, it's plus minus I, a e power I root k by m t plus b e power minus I root k by n t. Now, this should confuse you a little bit. At least it confused me when I first saw this, because it has complex numbers, and in general, x is going to be a complex number. But we are dealing with real objects, real displacements. So how to reconcile these two things? How can we make this a real number? The answer is the fact that the moment we started considering complex functions, like e power I root km by k by m t, the moment we started considering functions of that type, we left the realm of real numbers. Now everything we use is going to be complex, just like these two constants, a and b. So when the roots of this equation are complex numbers, the constants are also going to be complex numbers. And once you accept that, then it's easy, because then you will get real parts, and you're going to get complex imaginary parts. Then you'll set the imaginary part to be 0, and finally you will get your answer. People probably some people probably remember that the answer finally looks something like x equal to a cos root k by sorry, root k by m t plus, sorry, I think I should not use a here. Let's say c cos root k by mt plus d sine root k by mt. And this is obtained after breaking this down into real and imaginary parts and setting the imaginary part to be 0. When we are dealing with a difference equation, that means a linear recurrence relation, and we get complex roots for the characteristic equation, the idea is similar. Everything is the same. You set the coefficients to be complex as well. You separate the real and the non-real parts. You set the imaginary part to be 0, and you are done. Okay. By the way, you must have noticed that differential equations and recurrence relations are very similar. They are indeed, because they are both part of something called a dynamical system. Okay, and that's a subject that's very close to my heart because I actually do research on that. So I keep coming back to such problems. Anyway, now let's go to this problem. Actually, in this particular problem, I mean, this one, the problem we're solving right now, I was initially reluctant to use complex numbers. So what I did is I noticed that every Pn can be written as a linear combination like this: Fn P1 plus Gn P2 plus Hn P3. This is something you can easily verify. Okay, just write down some numbers and you will see everything is going to be a combination of P1, P2, and P3. And you can further check that each of these functions, Fn, Gn, Hn, which are real valued functions, by the way, they also satisfy the same recurrence relation. 2Fn equal to Fn minus 2 plus Fn minus 3. So I did this, and then I thought, hey, now we have a real sequence. Now let's do that solving. But when I solved, I saw that the roots were non-real. Then I thought, okay, we'll have to do with complex numbers anyway. So why not do it from the beginning? Okay, so I abandoned this idea and I did it directly. I solved this equation directly instead of breaking into Fn, Gn, Hn and solving the equation for F, G, and H. I'll erase this just to avoid confusion. So 2Pn is equal to Pn minus 2 plus Pn minus 3. This is a linear recurrence equation, and the solution space is clearly three-dimensional because you need three initial conditions. You need P1, P2, and P3 to determine the sequence forever. Okay? So let's see if we can find three independent solutions to this. Then any solution is going to be a linear combination of those. Let's see if there is a solution of the form, say, Zn equal to lambda power n. We get, substituting, we get 2 lambda power n is equal to lambda power n minus 2 plus lambda power n minus 3. We can cancel lambda power n minus 3, and that gives 2 lambda cube is equal to lambda plus 1. And I actually observed here that 1 is a root. Okay, because in general, solving cubics is quite hard. It's possible, but it's quite hard. But in this case, I observed that the 1 is a solution, so that facilitated my life. I just factored it like this. And yeah, that was it. Therefore, lambda is equal to 1 or minus half plus minus I by 2. I would like to make an observation here, which is that if I take 1 by root 2 common from the last two roots, that gives me 1 minus 1 by root 2 plus minus I by root 2. And these are actually 1 by root 2 e power I 3 pi by 4 and 1 by root 2 e power I 5 pi by 4. By the way, e power I theta is actually cos theta plus I sin theta. And that's a very, very non-trivial fact. I think it was proven by Euler. And that is far beyond our scope. We are not going to prove it. We are not going to discuss it. But just so that you know that it's very, very non-trivial, I'm mentioning this, okay? And the reason I wrote the roots in this form is that these two lie on the unit circle. Their absolute value is 1. And you will see why that is important. Therefore, the general solution looks like Pn is equal to some A plus some B times e power I 3 pi by 4 by root 2 whole power n plus some C e power I 5 pi by 4 by root 2 whole power n. Note that some e power I theta by root 2 has absolute value equal to 1 by root 2, and therefore the nth power of this has absolute value equal to 2 power minus n by 2, which actually goes to 0 as n tends to infinity. Therefore, as n tends to infinity, both these terms become insignificant. They go to 0. The only term that remains is capital A. Therefore, this sequence of complex numbers actually has a limit, which is A. Pn tends to A as n tends to infinity. What does that mean? I don't know if all of you are familiar with actual definition of limit, the actual definition of limit which involves intervals and balls and epsilons like that. It's basically like this. It means that choose any small number epsilon and draw a ball of radius. Ball in this case is a circle of radius epsilon about A. How much is the area of that? It's pi epsilon square. If Pn tends to A, then eventually means after a certain point in a sequence, all the terms are inside that ball, no matter how small epsilon is. If you fix epsilon, if you fix a ball about A, eventually all the points are going to be inside that ball. That means eventually all such areas mean Pn, Pn minus 1 and Pn minus 2. Eventually, all such areas are going to be pi epsilon square. And epsilon can be made to go to 0. Therefore, no matter how small you want to make the area, you can make it. You can make the area arbitrarily small by choosing epsilon to be very small. That means the area actually goes to 0. This problem actually has a second part as well, but we are not going to prove it. I actually didn't even write down the second part because that is very different. That has nothing to do with this chain of thought. Anyway, this was it for today. And if you have any questions, any comments, please talk to us. Let's have a discussion in the comments. Okay. See you later. Bye bye.